Hello students, welcome to EPG Pathshala. I am Dr. Rajiv Jain from Jivaji University Gwalior. Today we are going to discuss about the module acids, bases and their salts and complexes from paper Fundamentals of Analytical Chemistry. The very polar water molecule has a dielectric constant of 78.5. That is why this water molecule, this water is considered as universal solvent because it has a very high dielectric constant. Buffers typically consist of mixtures of weak acids and their conjugated bases or of weak bases and their conjugate acids. The buffer capacity of a system is defined as moles of strong acids or strong bases required to change pH of 1 liter of buffer solution by 1 unit. Inert solvents may be added to either protogenic or photogenic solvents to modify differentiating different types of titrations. The properties of aqueous solutions of acids and bases and their aqueous chemistry is of fundamental importance to chemistry and other related branches of science. The free hydrogen ion concentration dominates many chemical reactions by determining the extent to which the reaction proceeds, the rate at which it goes, or the detailed mechanism by which it takes place. Figure Figure 1 shows the monoprotic system. Monoprotic system, one proton is involved, movement of one proton. Here, reaction of acid with base is taking place and there is a movement of one proton and water molecule is being formed. The properties and reactions of aqueous solutions of acids and bases are fundamental to all branches of chemistry and related sciences. The free hydrogen ion concentration dominates many chemical reactions by determining the extent to which the reaction proceeds, the rate at which it goes, or the detailed mechanism by which it takes place. Figure 1 shows the monoprotic system. Only monoprotic system is shown here, and it has been shown that when acid and base are added, they form salt and water. The titration of a base with an acid is one of the simplest of all analytical determinations and is one of the first experiments to be studied by a student. It starts from class 9 how to titrate acid into bases, and in table 1 common definitions for acid base system are given. Here a definition is acid base neutralizations given by Arrhenius, Broughton, Lowry, and Lewis are given in table and summarized in table 1. For most of the purposes, Bronsted concept, as shown in figure 2, is the most useful. In this model, when an acid donates its proton, the remaining fragment becomes the conjugate base of the original acid. If the conjugate base accepts the proton, it reverts to the parent acid. Likewise, every base has a conjugate acid. For example, acid will form H plus plus base. HCl will show H plus plus chloride ion. NH4 plus plus show H plus plus ammonia ions. As we are shown here according to Lewis, according to Bronsted, and according to Arrhenius, they have been explained in figure 2. In the strength and overall defining acids, bases, salts, etc., the role of the solvent is very important. Free protons do not exist under normal conditions. Therefore, an acid cannot donate its proton unless a base is present to accept it. Many solvents, including water, possesses basic properties, that is, they can accept protons. Thus, when pure HCl is dissolved in water, a proton transfer reaction takes place. HCl plus water carbonic reactions, it will form H3O plus and chloride ions. Acid 1, HCl, base 2, H2O, acid 2, H3O plus, acid 2, and chloride ions are base 1. H2O, H3O plus, and HCl-Cl minus are examples of conjugate pairs. Acid-base reactions involve the transfer of proton. However, usually this is only a partial transfer, and there is a competition between two bases for the proton, as shown in the following equation. Acetic acid, abbreviated as HOAC, in the above reaction, the OH and OAC ions compete for the position. The OH ion is a much stronger base than OAC minus, and therefore the equilibrium lies far to the right. Therefore, equilibrium far to the right. A comparison of the two reactions just given shows that the water can act as either an acid or a base depending on the acidic or basic nature of the other partner in the reaction. Water is an amphoteric substance and it is also an amphiprotic solvent. Amphiprotic solvents undergo autoprotolysis or self-ionization, a proton transfer reaction where one solvent molecule donates a proton to the another solvent molecule. Water is the most familiar example, but there are many others also. H2O plus H2O form H3O plus plus OH minus. Acid 2 H3O plus and base 1 OH minus. Similarly, C2H5OH plus C2H5OH, it will form C2H5OH2 plus C2H5O minus. Similarly, in ammonia NH3 plus NH3, it will form NH4 ammonium ion plus NH2 minus ions. Solvents are classified with respect to acid-base properties as either aprotic or amphiprotic solvents. Aprotic solvents are neither acidic nor basic. Amphiprotic solvents act as both proton acceptors and proton donors. There are gradations among the amphitropic solvents from predominantly acidic to predominantly basic. Glacial acetic acid is very acidic, whereas liquid ammonia is very basic. Water and ethanol are neither strongly acidic nor strongly basic. Protogenic amphiprotic solvents exhibit very strong acidic properties and very weak basic properties. Autoprotolysis constants for protogenic solvents are usually larger than that of water. Intermediate amphiprotic solvents possess weakly acidic protons and can also act as very weak bases. Autoprotolysis constants for non-aqueous intermediate amphiprotic solvents tend to be smaller than that of water. Protophilic amphiprotic solvents exhibit very weak acidic properties and relatively strong basic properties. Their autoprotolysis constants are usually less than that of water. Dielectric constant effects. The strength of an acid Hb in a given solvent SH is defined in terms of the extent to which the reaction Hb plus Hs in equilibrium forms SH2 plus B and it proceeds. This reaction is a combination of two steps, ionization and distillation. In aqueous solutions, both of these steps occur rapidly and aqueous acid-base reactions are thus very fast reactions. In any solvent, the extent of the ionization step depends on the relative strength of the conjugate acid conjugate base pairs. The extent of the dissociation step depends on the charge type of the members of the ion pair and the polarity of the solvent. The dielectric constant is a measure of this polarity. The higher the dielectric constant, the more polar the solvent. The extent of dissociation of ion pair aggregates increases with the dielectric constant of the solvent. Clearly, then, solvents with high dielectric constants are necessary for complete dissociation. The dielectric constant of a vacuum is arbitrarily classified or is arbitrarily defined as zero. The very polar water molecules has a dielectric constant of 78.5, whereas the value of the slightly polar acetic acid molecule is 6.2. The conjugate pair has been illustrated in figure 3. The relative strengths of different acids can be measured by comparing their ability to donate a proton to some common base. Likewise, the relative strength of different bases can be measured by comparing their ability to accept a proton from some common acids. Water is selected as both the common acid and the common base for these comparisons. The quantitative measure of this strength is the equilibrium constant for the appropriate proton transfer reaction. Equilibria in monoprotic systems may be discussed or may be evaluated mathematically by using the following treatment, which I shall explain in following equations. Calculating hydrogen ion concentration or pH in a number of acid systems as shown in figure 4 in water give us a means of estimating pH in various solutions. The following conventions have been used. The hydrogen ion is represented as H3O plus is used interchangeably with the hydrogen ion H plus. In the derivations you have seen, which we have derived for monoprotic systems, equations 5 and 9 are known as Henderson-Hasselbalch equation, which are very important equation while deriving for monoprotic systems. All of the above equations neglect the contributions to H plus and OH provided by the autopyrolysis of water, because water itself is autopyrolytically gives H plus ions and OH minus ions. These contributions, which can never exceed 10 raised to power minus 7, are too small to take into account except in highly dilute solutions. So here is the convention how we treat the monoprotic system, how by its pH may be determined by taking hydrogen ion concentrations and OH negative hydroxyl ion concentrations, and what is Henderson equation, Henderson-Hasselbalch equation, which is a very important thing. And the another point to be noted that the contribution of H plus and OH minus should be avoided, which comes from water by its autoprotolysis. By the autoprotolysis decomposition, water gives H plus and OH ions, OH minus ions, which should not be taken into account. Buffer solution. Many chemical reactions generate free hydrogen or hydroxyl ions. If these ions remained in the system, there would be significant changes in the pH. Buffer solutions contain constituents that react with both strong acids and strong bases in such a way that the free hydrogen ion concentration of the system remains relatively constant. Buffers typically consist of mixtures of weak acids and their conjugated bases, or of weak bases and their conjugate acids. Buffer capacity. Buffer solutions resist changes in the pH upon the addition of strong acids or strong bases. The buffer capacity of a system is defined as the moles of strong acid or strong base required to change the pH of 1 liter of the buffer solution by 1 unit. The larger the buffer capacity, the better the buffer. That is, the more acid or base it can consume without significant changes in the pH. Clearly, more concentrated buffer solutions have higher buffer capacity than more dilute solutions. For example, even though a solution that is 0.0100 F in both acetic acid and acetate ion has the same pH as a solution which is 0.100 F in both of these constituents, the more concentrated solution can consume 10 times as much strong acid or strong base for the same change in pH. Now, after understanding the some fundamental terms, we shall here start with the acid-base titrations in aqueous solutions. One of the principal reasons for mastering pH calculations is to be able to use them in predicting and analyzing titration curves for acid-base reactions. A titration curve shows how the pH of a solution changes upon the addition of acid or base. If it is a plot of pH versus volume of titrant added, the region near the equivalence point is of special importance. The inflection point, which occurs at the steepest portion of the curve, coincides with the equivalence point. The steeper the curve, the sharper the endpoint, and the more accurate the titration will be. Titration curves be obtained experimentally by measuring the pH with a pH meter after adding successive increments of titrant. Titration curves for strong and weak acids and bases are plotted and has been shown in figures 6, 7, 8, and 9. In calculating points for these curves, it is helpful to use generalized formulas such as the following, in which V0A, V0B, C0A, CB are the initial volumes and concentrations of acids and bases, and VA and VB are the volumes of titrant, that is, acid or base, added at any point. If you keenly observe the titration curves, a number of useful observations can be obtained from these titration curves. For example, note that pH change near the equivalence point is considerably smaller in the weak acid titration than in the strong acid case. The magnitude of the pH break depends on the concentration of reagents in the strong acid case, whereas for weak acids, the magnitude of the pH break depends on the Ka of the acid unless the solution is very dilute. Titration of weak acid with a weak base is unsatisfactory and unnecessary since a strong titrant can always be used. These curves clearly indicate that if Ka or Kb is less than 10 raised to power minus 8, there will be difficulty in locating the equivalence point even with a pH meter. Such weak acids and bases are best titrated in non-aqueous solvents. Another very important requirement for acid-base titrations are indicators. Because solutions of the common acids and bases are colorless, thus colored indicators are useful to detect the endpoint of their titration. Acid-base indicator, as given in table 5, are intensely colored weak acids or weak bases whose conjugate form has a different color. A small amount of the indicator is added to the sample and is titrated along with it. An indicator is selected that is just half titrated at the pH of the equivalence point of the main titration. The indicator will exit half in its acid form and half in its basic form and exhibit an intermediate color. Thus, this results if the pK of the indicator is close to the pH at the equivalence point. pH equivalence is equal to pKa plus log Cb upon Ca. In table 5, different types of indicators are mentioned for acid-base titrations at different pH. Acid-base titrations in non-aqueous solvents. Most of the non-aqueous titrations involve neutralizations of organic bases or acids and the direct determination of acidic and basic functional groups. In addition to their importance in organic synthesis, non-aqueous acid-base titrations are used extensively in pharmaceutical analysis, for example, to determine constituents present in antihistamines, antibiotics, and sulfonamides. Direct titrations are possible in non-aqueous acid-base reactions since they proceed to completion within a few microseconds. There are numerous advantages offered by acid-base titrations in non-aqueous media, the most important of which is that a much larger number of acids and bases can be titrated in non-aqueous solvents than in aqueous solvents. For example, a weak acid with a pKa of 9 or greater cannot be determined accurately in water because of the competition of the solvent for a strong base titrant, that is the leveling effect. But the weak acid can be titrated in ethylene diamine, which is considerably more basic than water. The availability of a large variety of non-aqueous solvents allows the choice of a solvent that will assist but not interfere with a specific acid-base titration. A properly formulated non-aqueous acid-base titration procedure provides results that are very accurate and often more precise than those obtained from a corresponding titration in aqueous media. We will consider briefly some of the practical considerations that apply to non-aqueous acid-base titrants. Since perchloric acid is the strongest mineral acid, acidic titrants normally consist of solutions of perchloric acid in either anhydrous acetic acid or dioxane. Acidic acid solutions that are 0.1 to 1.0 F in perchloric acid commonly are used. Perchloric acid is essentially 100% ionized in acetic acid. It exists as the ion pair H2, H2O AC plus ClO4 minus as well as the solvated ion H2O AC plus. Basic titrants include quaternary tetraalkyl ammonium hydroxide, which are stronger bases than the alkali metal hydroxide. Although the product salts of alkali metal ions are quite insoluble in non-aqueous media, quaternary ammonium salts are very soluble. Tetrabutyl hydroxide in isopropanol is the most commonly used base titrant. To ensure that the titrant's solvent does not interfere with the principal reaction, the concentration of the titrant solution is usually high relative to the concentration of the substance titrated. Only a small amount of titrant is added compared to the volume of the titrant mixture. Choice of solvent for acid-base titration. The following considerations are very important to the choice of a solvent for a specific non-aqueous acid-base titration. The solvent should permit a large change in the solvated proton concentration near the equivalence point. Other things being equal, the smaller the autoprotolysis constant, the better the endpoint. The substance to be titrated must be soluble either in the solvent or in an excess of the titrant, which they may be back titrated. The product of the titration must be soluble, or if it is a precipitate, it must be compact and crystalline and not gelatinous. Gelatinous precipitates tend to interfere with accurate endpoint determinations. The solvent should not introduce interfering side reactions with either the substance to be titrated or with the titrant. Preferably, the solvent should be inexpensive and easily purified. Many of these solvents are toxic and require special precautions in handling. Inert solvent must be added to either protogenic or protophilic solvents to modify differentiating titrations. The presence of the inert solvent decreases the amphiprotic character of both acidic and basic solvents. For example, butylamine and pyridine are both titrated as strong bases in glacial acetic acid, but in solvent which consists of 10% acetic acid and 90% chloroform, two distinct equivalence points are noted corresponding to the neutralization of butylamine and then pyridine. Normally, the titration of a weak acid in an inert solvent involves the addition of a small volume of concentrated base dissolved in an amphiprotic solvent such as an alcohol. Thus, after the first addition of titrant, the system contains a small amount of amphiprotic solvent in an inert solvent. The effective autoprotolysis constant for the system is that of the amphiprotic solvent mixed with the inert solvent. When the amount of amphiprotic solvent is small, the effective autoprotolysis constant is small and the pH break is larger near the equilus point. This is the reason why highly concentrated solutions of bases are used as titrants. Isopropyl alcohol is commonly used as the solvent for tetraalkyl ammonium hydroxide because it is the least acidic of the amphiprotic solvents. While doing titrations for monoprotic systems, in non-aqueous systems, determination of endpoint by potentiometric method is a choice. In a typical non-aqueous potentiometric acid-base titration, following cell is used, which involve a glass membrane having a silver chloride in equilibrium with the saturated calomel electrode, or we can say, if I say that following glass membrane electrode is used. As in aqueous solution, the glass membrane electrode appears to respond to the difference between the activity of the solvated proton in the solution inside the glass membrane and the activity of the solvated proton in the solution on the outside. Ion activities in one solvent cannot be simply related to ion activities in another solvent. In addition, when we measure the EMF of the cell just shown, we include a sizable unknown liquid junction potential between the aqueous calomel electrode and the non-aqueous solution. Liquid junction potentials must remain reasonably constant during the course of the titration for high precision. There should be no high liquid junction potential. Liquid junction potentials must remain reasonably constant during the course of the titration for high precision. So for titrations in ethanol or glacial acetic acid, the glass electrode system appears to respond to changes in minus log ethanol and minus log acid H2O AC plus as shown in the following equation. When an acid is titrated in an inert solvent, that is a ketone with tertiary butyl ammonium hydroxide in isopropanol, the glass electrode responds to changes in the isopropanol solvent proton concentrations. In highly basic solvents such as butylamine and ethylene diamine, the glass electrode does not function as an indicator electrode, and antimony electrode is used instead. In some cases, some chemical indicators have to be added. Indicators for non-aqueous acid-base titrations behave similarly to those that are employed in aqueous titrations in either giving up or accepting protons and changing color in the process. An indicator therefore may dissociate in solvent as such, like as given in the following, that color A, first it is A color and then it changes to color B. Clearly, the predominant form of the indicator in the above equation depends on the SH2 cation concentration. However, in non-aqueous media, many solvents are available and the behavior of a particular indicator depends on the acidity, basicity or inertness of the solvent as well as its dielectric constant. Some indicators have simply color changes, others successfully pass through the wide range of color shades. So students, today you learned about the acid-base titrations, which may be aqueous acid-base titrations when we take them. Acids and bases are taken in aqueous systems. Usually water. Why water is preferred? Because it has very high dielectric constant. Dissociation of protons and OH ions are freely available. And on the other side, when other types of titrations are done, which is not possible in aqueous system, such as weak acid and weak base, where we have to, for increasing the activity, we have to take non-aqueous system. So for non-aqueous systems, we find it is difficult to observe the endpoint. In that case, endpoint is observed by different methods, for example, by potentiometric titration. So we may summarize, or in summary we can say, For titrations of weak acids and weak bases, inert solvents provide the largest break in pH near the equivalence point. Inert solvents are also preferable in successive titrations of acids and bases in mixtures. When solubility problems are encountered with inert solvents, protogenic solvents are used for weak base titrations and protophilic solvents are used in weak acid titrations. The Bronsted concept is the most useful. The concept of Bronsted is always to be kept in mind when doing either titrations in aqueous solutions or in non-aqueous solutions. Thank you.